You are in for a treat. The Grubbs olefin metathesis is a great reaction. And it's a relatively recent development. Here's a photo of Bob Grubbs here. He got the Nobel Prize for this accomplishment back in 2005, way back then. And he's at Caltech and developed the catalyst that allows this carbon-carbon bond forming reaction between olefins, as you guessed it, to occur. Many variations of his catalyst and as so-called second generation, third generation Grubbs catalyst have since been made. We're going to focus on one. And what do I mean by catalyst? Look what's over the arrow. Look at this beast. So this looks like a simple enough reaction, but don't let it deceive you. It's a whole lecture for a reason. Not a long one. But I'm keeping it by itself because it's deceptively simple looking. Okay, alkenes in, alkene out. So what really happened there, first of all? And second of all, equilibrium. So that plays a role in some of this. And then what's over the arrow? So that's the part that might be scary. So right now this is simplified, and we'll expand on this with a specific example because this is way too simple to see what's going on with just the R groups. But at the very least, we can get a glimpse. So notice that the carbon with the regular R groups versus the carbon with the primed R groups, they started off separate, and then, so aha, something did change, right? We got an alkene. We didn't change functional groups. We swapped groups attached. Now look at this catalyst. This is the, let's do this in green, Grubbs catalyst. You see rightfully that it's kind of a lot to draw and remember. So let's just take a minute to appreciate what's here and how do they come up with these things, right? It takes a lot of trial and error as well as planning and predicting. Okay, so there's a lot of bonds to this central atom, which is an indication it's a transition metal. So what is this? Ru. Ru what? That's what you're thinking. No, we don't have a periodic table in this room. Usually I could point to that. I'm actually in a playroom, but I remembered I do have elements in here after all, in this basket. So yes, there's toys I'll have to dig through. So you can see there's these element blocks. So this could be sort of our periodic table, and my kids played with these and could even joked about some hazardous waste going by and whatnot. But let me see. I'm still digging for the RU. There we are. RU. So what is RU? There it is. Number 44. RU is ruthenium. Ruthenium, metal catalyst. So ruthenium is the important part of the catalyst. The ligands that are attached to it play a role. We're not going to focus on that, but they're going to be simple. We're going to simplify it to the ruthenium catalyst. It might be written as Grubbs in quotes sometimes over the arrow. So some different practice book sources will just say Grubbs over the arrow, or it will be simplified to something like what you see here, Ru, and then the pi bond. The pi bond is important for the mechanism. The rest of the ligands don't play a role in the mechanism, but they play a role in the stability and the reactivity and that sort of, which are really the same thing, right? So let's just take a minute to recognize this is a Grubbs catalyst. You might change the ligands and then study this in a different book and see that it should still have the same reaction, okay? But what ligands are we talking about for this catalyst? Chlorine, easy enough. Phenyl, PCY3, we addressed those as ligands before. Tricyclohexyl phosphine. So the heavy work is done by the Ru and the pi bond to the carbon here, and so that's what we will focus on. So it says you may use this abbreviation for the catalyst, Ru, with that, okay? So it's not the real structure, it's an abbreviated version. You want to draw the whole thing, that's fine, but just to make our life a little more efficient when we're drawing our mechanisms, so that is acceptable and common. Put those back. Okay, so how does this look? Now that we've simplified and taken some time to look at the catalyst, let's see how this reaction actually works. So we can have a self-metathesis where an alkene reacts with another alkene that is a copy of itself, its neighbor, because you never have one single molecule by itself. So what would that look like? 1, 2, 3. I'm numbering my carbons because I'm about to let it react with another one. So that means these would join together at this pot. So actually what I'm going to do is draw it in a way where I can show them kind of facing each other. So another version of itself, but we know that they join at the alkene. That's not all. I'm gonna draw the product and we're gonna see what's happening. So it's actually like this wiggly bond because it could be cis or trans. Okay, so that means we have this. Plus the trans. I hope you're screaming at me for dropping a carbon. I did drop a carbon, actually on purpose. So what happens is those internal carbons go off together in the mechanism, we'll see how, to make the byproduct, ethylene gas. Okay? So when I count my carbons when I'm done, even though I put 2 of them together, so I have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You expect 10 carbons. And yes, we will account for 10 carbons, but 2 of them will be gone as ethylene gas. So 5, 4, 3, 2, 5, 4, 3, 2. So the 2 carbon ones ended up over here. I'll make this 1' because that way I can distinguish between the duplicate numbers. All right, so you lose ethylene gas. So one way to think about it was when you can draw those alkenes facing each other and then kind of either circle the ethylene gas that's about to come off and exclude it, and also it might help to encircle the rest and realize that's going to be what makes up the final product and account for cis and trans. So that is actually a driving force because this is an equilibrium, evolving or evolution of the evolution of the ethylene gas. Okay, let's do the real mechanism. Complete mechanism. Here we go. It's going to be a catalytic cycle. So you may just want to get a piece of paper. I don't think this was enough room. I apologize. I could probably squeeze it in. I don't know if you want me to though. So I'm going to take up as much space as needed. May go well past that number at the bottom of the page, so that means you might need a piece of paper. I'm going to predict the product first using that method where we know the ethylene gas is going to go.
Break it down, let me see what you can do. Let me see you throw it down and
take our, what's going on here? There's only 1 alkene. No, there's not. There's 2 in 1 molecule. So say hello, intramolecular metathesis reaction. I'm going to cyclize that. Those will be gone. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. 8 minus those 2 carbons. Let's draw in black. Is 6. So carbon 7 and carbon 2 will join together in a pi bond. So this will be our product. So it'll be 7, 6, 5, 4, 3, 2. And then our ethylene gas are carbons 1 and 8. But it goes off. It's not always drawn as a product because this would be a ridiculously over-the-top expensive way to make ethylene gas. So it's not the goal. The goal is to do this amazing feat. I mean, just think about that for a minute. We would have had to use a Diels-Alder and generate the reagents that satisfy Diels-Alder conditions to get this particular ring. That would be a long way from here. If this was our starting material and this was the easiest thing to get to, it's cool to know that, hey, we have a olefin metathesis option to put two olefins together. Okay, so I'm going to abbreviate the catalytic cycle because it could be complicated with, I'm going to go back to using R groups, and then we'll see how it fits into this whole thing. So what I mean by that is I'm going to take my alkene. I'm just going to make a generic alkene like this. And then I'm going to show it interacting with the catalyst. The catalyst lines up with it. In fact, I'm actually even going to do terminal alkene. That's what I meant to do. Okay, so the catalyst is going to come along and interact with it. And notice it's lining up with the ruthenium toward the internal part. That's why I made this asymmetric, just to account for other cases. So it's lining up with the end, the internal part. So it's the bulkier part. So the end with the end, in other words. Okay, so let's push some arrows. So when it lines up like that, it does a 2 + 2 cycloaddition, which means we've done cycloadditions before. We're going to make a ring. So make this 4-membered ring. So because it's a catalytic cycle, I'm going to draw it in a big circle. And I'm going to write the name of the step around the curved arrow leading that way. 2 + 2 cycloaddition. All right, so now it's incorporating the ruthenium into one of the starting materials. Okay, so now the only thing left here to draw here is R. So notice that we made a cyclobutane type ring, 4-membered ring, with the ruthenium as one of the cornerstone atoms. So that's what those red arrows told us would happen. This collapses back down, but a different direction. So ruthenium is going to hang out with the main chain now, and that'll allow the main chain to release those carbons. Now let me draw in all those hydrogens here, because when I do that, it might become clear what's going on. Look, this, once this gains that extra bond, we've made ethylene. That's where ethylene departs from. So I'm going to show an arrow coming off here to indicate the departure of the ethylene. I'm going to write in blue since I circled it in blue. And now ruthenium is part of the big substrate. I'm going to write CHR. So it's this piece here, CHR, okay? All right, so you effectively have another version of the catalyst ready to go. It just swapped out what was attached to ruthenium, but this is still reactive. So we're going to throw in some more alkene for it to do that same thing with. And guess what? That's actually going to take us home. No, I need one more step to show. So let me shorten that arrow and fatten it a little bit. Okay, so I'm going to bring in some alkene. So let's bring that in here. It's going to be starting material. So we'll have a terminal olefin with an R group on one end, and I'm just going to box it so we know this is more starting material. Okay, so let's draw this in R. When it looks. Okay, so let's do the 2 + 2 cycloaddition. Here we have ruthenium again as one of the cornerstone atoms. Drawing in all the groups. And now we're going to collapse it back down such that the catalyst is regenerated and so is the product. So notice right here, if I collapse it like that, I make this catalyst again. So out pops the catalyst, and guess what else comes out? I'm going to draw it as a product of the catalytic cycle. Our actual product. This one right here is going to be CHR, double bond, CHR. Cis and trans, of course. So I write the both. So that's the final product. Pretty cool, right? So when it is cyclic, we don't throw in more starting material separately. It just comes from the own thing wrapping around back, but it's the same mechanism. Oh, that was it. So what I'm going to do now is examine where this usually goes wrong. Okay, so you say simple enough. Let's do that mechanism again. I'm going to zoom in on two main ways to start the mechanism. So this is, if you didn't need another piece of paper, now you really will. Let's do one more example actually, where we instead of doing an R, I'm going to say let's do the mechanism for the original one that we had here. Let's do that mechanism. So mechanism with this one. We need to show the mechanism. Okay, so this was the other problem given to you. Now, first I take my ruthenium and I've got to line it up. And I remember I said it has to be end to end or not end to end. Let's see what happens, how we can prove why it needs to be one or the other. So let's take our starting material, and we either are going to let the R group be toward the ruthenium, so that isopropyl that's coming off, or actually let's kind of set up like a battle versus are you lined up the other way where that R group is kind of out here instead. Okay, see the difference there? So I put the RU on the left, but the isopropyl is also on the left, or they're on opposite sides. Let's do that cycloaddition. So it's going to make this like 4-membered ring, right? That cycloaddition. Doesn't matter which direction you go or which one you push first, really. So now, RU in the corner, next door to the isopropyl, versus ruthenium in the corner, diagonal from the isopropyl. Interesting. We're starting to see the difference. So the key step of the mechanism is that this breaks back down. So let's break it back down. We got to break it down so that we, remember in the first step, we evolve ethylene gas. So how can we evolve ethylene gas? Well, you got to push it that way, right? Because this would be our ethylene gas right here. Yeah, that works. And there's something wrong, seems wrong with drawing ethylene as two parallel lines. That's, at that point, I feel like I do need to draw on the carbons. It's hard to see what it is, but you can leave it that way. So this would be the resulting products for that step. Then it would keep going. This would go on, and we will do that because it's worth doing another mechanism just for good practice. Now, What about that? Let's break it down. Well, where's that ethylene going to be? Don't see anywhere. Because it's diagonal, it's kind of messed up the chance for any of the two carbons to get together. If I break it down here, I have this alkene. If I break it down here, I have that alkene. So we have to do something. But the thing is this happens. It's reversible. It's an equilibrium. But what happens when that happens is, look at what those arrows tell us. Did that give us ethylene gas? No. Did that give us our product? No. What did that give us? Starting material and starting material. We're back where we started. So the moral of the story is, it's not wrong to draw that path because it happens. It just does not progress the reaction. So it is not the mechanism for the reaction. It happens, but when you start doing it, you don't have to be paralyzed by fear that you're going to do it the wrong way. You start doing it, and then you realize this is getting you nowhere. So you're going to have to flip their alignment. Simply head to head versus head to tail, essentially, right? Okay, so let's see how that fits in the catalytic cycle. Once you get the ethylene gas evolved, that's ready to go with another piece of the starting material. So why don't we just complete the mechanism while we're at it? Why don't you complete the mechanism? You do it. I'm gonna get you started. Okay, so starting material comes in, which is more of the plain old boring, non-rutheniumated, if that's a word, alkene. So in it comes. What do? You're gonna do a 2 + 2 cycloaddition. This time line those up. Do that step carefully. Say, do I need to do this? Or leave that one the same, but flip this one. Which one? Remember what your goal now is not to make ethylene gas. Your goal is to make the product, to get those two R groups together. So when you draw those, it can be easy to draw one the wrong way if you're not thinking about it. So you have to pick the correct orientation that will give you the product. Give it a try.
Line up, everybody, line up, line up, line up, my line up, everybody, line up, line up, line up, my. Here we go, everybody, line up, here we go, outside. Everybody, let's go, go, go.
Okay, so I know that required some problem solving, but that's a good thing because that means you don't have to memorize weird four-membered rings as part of the mechanism. You can work it out. So what did you get? Well, the proof is in the pudding. You gotta push those arrows and see which one makes the most sense, right? So we have our four-membered ring this way with adjacent R groups versus our four-membered ring this way with diagonal R groups. Well, the diagonal is bad news. Once again, that will not get us anywhere. That'll get us back to starting material. Prove that to yourself. So let's put this one in. We need them adjacent in order to get a pi bond between them, right? I'm going to break that back down. So RU's here, plus and we did it. So this one goes on to repeat the cycle. And that is our final product. Ta-da! I hope you enjoyed Grubbs ring closing metathesis. That's what this is called. When you have a, Grubbs metathesis, olefin metathesis. When you have a ring, we call that Grubbs ring closing metathesis. There's also a ring opening metathesis because it is reversible, but we're going to focus only on the ring closing. So this is RCM, ring closing metathesis. not ring closing meat. Ring closing metathesis. You might want to add that term next to your notes with the ring. Cool applications you can imagine doing with that. And the best way to probably practice these problems is to do a lot of not just predict the product, but also do the mechanism a few times, especially the step where you have to decide how to orient that part. And then it'll be a lot more clear what's going on.